Traversing a tree means accessing all the nodes of a tree. There are three ways a tree can be traversed: in order, pre-order, and post-order. In pre-order traversal, the root of the tree is visited first and then the left and right subtrees are traversed respectively. In order traversal, the left subtree is traversed first, then root of the tree and finally right subtree. In post-order traversal, the left subtree is traversed first, then right subtree and then root of the tree is visited. Let's see each using a sample example. Let's see the result of pre-order traversal on this tree. So, basically, in pre-order traversal, nodes are printed as soon as they are reached. Once printed, they are not printed again. Now, let's see the result of in-order traversal on this tree. In in-order traversal, we will traverse the left subtree first, till the end. Then print the node, and then traverse the right subtree. An easy way to say that would be: don't print the node when it's reached first time like we did in pre-order traversal. Instead, print it when reached second time. Finally, let's see the result of post-order traversal. In post-order traversal, we traverse left and right subtree and then print the node. In short, we print the node when it's visited third time. Let's see it using the same sample tree. A binary search tree is a binary tree which satisfies two properties. Element in the left node is smaller than the current node. Hence, all elements in the left subtree are smaller than the current node. Element in the right node is greater than the current node. Hence, all elements in the right subtree are greater than the current node. This is a sample binary search tree. You can see each node satisfies the two properties. If we have n elements in a binary search tree, time taken to search an element in the tree will be somewhere in between O of 1 and O of n. Let's try to prove it. Searching any element will result in locating that element from root node till a leaf node if search is successful. Otherwise, even after reaching leaf node, element cannot be located. That means, in best case element isn't root node, hence O of 1. And in worst case element is one level before the leaf node. So, in worst case search will cover entire height of the tree. From previous slides, we know that in a binary tree, height will always fall between log of n plus 1 minus 1, and n minus 1 divided by 2. A worst case tree will have height equal to number of nodes. Hence, worst case search will be O of n. So, number of comparisons will always fall between O of 1 and O of n. At a very basic level, 3 primary operations are possible on a binary search tree. And when we say binary search tree, we mean it will have 2 children, and follow the properties of the binary search tree, as mentioned in the earlier slides. Insert, delete, and is external. A simple linked structure for a binary search tree would be: it will have pointers to 2 children, left and right, and space for the element to be stored. However, if you remember, in a previous slide we talked about an operation, sibling. In order to find the sibling of a node, we need a way to find the parent of that node. Which means, we need another pointer in this linked structure, to point to the parent. So, this linked structure will change something like. However, in this example we will demonstrate only the use of the first structure. We will see how to implement a binary tree using the linked structure. First, let's see what each of those 3 operations will do. Insert will insert an element in the binary tree, and change the structure of the binary tree. Delete will delete an element from the binary tree, and change the structure of the binary tree. Is external on a node will tell whether it's a leaf node. On both insertion and deletion of an element we have to ensure that the resultant tree, after insertion or deletion, maintains the property of the binary search tree. While inserting an element we check for binary search tree property and propagates the new element to either of left or right subtree. Once we have reached the leaf node, actual insertion happens. And while deletion we make sure one of the left or right children occupies the current node. Let's see few insertions and deletions on an empty binary tree. The tree is initially empty. So, pointer tree will point to null. An insert of 9 happens. A new node is created and 9 is inserted into that. Its left and right pointers will point to null. And tree pointer will point to this node. Then an insert of 3 happens. It will start from the top of the tree, and go until a leaf node has been reached. A temporary pointer is used to track this. The new node will go to either of left or right subtree of this temporary pointer. So, at the start, temp is pointing to the 9. The new element is compared with temp. Since 3 is less than 9 we will move to the left subtree. Since left subtree is a leaf node, we will insert 3 there. If it was not a leaf node, we would have moved further down the subtree with a similar kind of comparison. A new node is created and 3 is inserted there. Left pointer of temp will point to this new node. Then an insert of 6 happens. Once again, it will start from the root node, so temp will point to the root node. 6 is compared with 9. So, I will go to the left subtree. So, temp will now point to 3. 6 is then compared with 3. So, it should go to right subtree. Since right subtree is null, the new node will be inserted there. One more insert happened with 13. You can see how tree changes.